Hello student, how are you? I hope you all are happy, healthy and very fine at home. What did we discuss yesterday? Yesterday we discussed about the transfer of chirality, and what we are going to learn today, that is as well as yesterday we discussed about the scaffold process, and today what we are going to discuss, today we are going to discuss about the extended and the fused structure, that is the scheme number 10 one, and it is shown on the blackboard. Let us look at here. L erythro, B hydroxyhistidine. It is one of the natural product, or what we can call it is a medicinal, or it is a one of the drug useful, and how we can synthesize this natural product in the laboratory by using as a appropriate or the suitable precursor. And as we know that here, while studying as a Chiron approach, we should keep in mind there should be as a Chiron approach, don't go anywhere. So you fix your that target molecule applying the Chiron approach, and we are looking here the extended and the fused structures. So that are the L, as we know that L are the relative configuration when it is generally referred for carbohydrate and the alpha amino acid, and as we know that natural carbohydrates which are present in the D series, whereas the natural amino acid they are present in the L series, and therefore it is a L. If you write this structure according to us, and generally these carbohydrate as well as amino acids generally drawn on the blackboard or in the book, generally they are according to the Fischer projection formula. There are the certain rule to represent that molecule on a blackboard or in the black. So on that basis we can decide whether it is a L configuration or the R configuration. So it is a L configuration, it means that amino groups are present on the left hand side, and therefore this is erythro. Erythro means again there are the two relative functional group if they are present on the two chiral centers are there. If the both functional groups are present on the same side on the basis of the Fischer projection formula, then we can call it as a erythro. And trio means what? Two functional group are opposite to that carbon skeleton or the carbon framework. That type of the conformation is called as a trio, and this is a the histidine shows as a biological activity, is a very useful molecule or the natural compound. And now if you see here retro, and as we know that this is the disconnection arrow. Disconnection arrow means what? The disconnection means what? The analytical operation which break a bond and convert a molecule into a possible starting material is known as a disconnection. So according to that, if you look at this and we are keeping here is a carbohydrate type of symmetry. Clearly you can see over there, as well as there is a one NHR, means there is a amino group. This is alpha amino hydroxy group you can see here, as well as the partial aldehyde group as well as hydroxy group also present over there. So this is the segment, or it is a what we can call it is a partially hidden carbohydrate symmetry as well as alpha amino type of the compound is present over there. So this is the what we can call it is a Chiron, and this compound can be obtained from this, and it is just like as a what we can call as a 5-membered lactone type of the compounds are there. Here had a carbonyl group and the oxygen atom, if they are present in the cyclic form, that type of the organic compound is termed as a lactone, and this is a this is not the complete skeleton of the carbohydroxy type, but it is amino, NH amino also there, and it is a hidden over there in this particular case. And this compound, this type of the compound can be obtained from this, and this is if you invert this amino group, that is the name of this compound is known as a 2-amino 2-deoxy D-glucose. And after inverting means what? You can change its configuration. If this compound has a R configuration, after inverting you should get the S configuration. So that type of the process is known as a invert process, and this is a carbohydrate type of the symmetry present over there. So in this way we can see the extended and the fused structures. And in some target a segment of the carbohydrate portion may be utilized to construct an integral part of the structure, and thus in the synthesis of the imidazole ring in L-erythro beta hydroxy histidine, which is written on the blackboard, a component of blomycin from 2-amino 2-deoxy D-glucose. 2-deoxy means there is a no hydroxy group, D means remove, oxy means oxygen atom, and 2-amino 2-deoxy D-glucose, 2 carbon atom of the carbohydrate were extended and into the heterocyclic structure that is shown in this scheme. The remaining appendage comprise C1 to C3 of the original amino sugar is present with its intact functional groups and stereochemistry. Hence the partially hidden symmetry. And there are a number of other heterocyclic structure which can be built from segment of carbohydrate. A different situation arises in some target in which the carbohydrate symmetry is of the hidden type. It is not clear, you cannot see clearly, there is a partially or it is a hidden symmetry present over there. And consider for example thiomycin, scheme number 11, which can be related to L-ascorbic acid and L-threonine as a chiral synthesis or the precursor. Let us see here the structure of that. Now we are going to see how the extended and the fused structure. Now let us see the structure of this is this one. Here is a nitrogen atom 4-membered ring present over there, and this is a lactone type of the ring present over there, and here is a 5-membered ring, and there is a double bond and CO2H carboxylic group. It is one of the functional group present over there. Then sulfur, and then again in a extended case we are getting as a NH2 group, and here at a junction there is a hydrogen atom which is below the plane, and at this junction again the hydrogen atom which is coming toward us means it goes above the plane, and now here is a hydroxy group. Thick line indicate that OH group is above the plane, and here is a Me means this is a methyl group. The name of this compound is a thiomycin. This is a structure of thinamycin. This is a structure. This is a structure shown over here. This is a scheme number 11 over here. Scheme number 11 shown in this case. And now from this, if you see, here is a disconnection, as just now we have seen disconnection process. It is a process where we can convert the molecule into a possible starting material by breaking the suitable structure. So now the skeleton we are getting over here. This thick line I am showing over here. Look at carefully. And now here is a methyl group, and here again is a hydroxy group, and at this corner point there is a NH2, and here is a carboxylic group CO2H. The skeleton present over is a alpha hydroxy alpha amino compound. This one L309. This is known as a L309. 309. This is the structure of L309. Or we can draw this structure in another way. We can represent this structure in this way also. And look at here the carbon skeleton. It is like this. Here you can put CO2H, and at this corner point here we can connect NH2 group. Again show the hydrogen atom that goes below the plane, and this carbon atom O2H, that is the carboxylic group. This side as well as this side, that is the structure, one of the structure of amino acid, which is known as a L-aspartic acid. This is a L-aspartic acid. This is a structure of L-aspartic acid, which is, and this is a L309. They are the amino acid, and which is present here. They are not clearly seen here, but they are partially, or it is completely hidden over there. Now if you see the retro of this, what do you get here? You will get here this type of the carbon skeleton over here. This carbon skeleton also present over there, not like this. Let us see here completely. This one, there is a thick line shown over here, and then this thick line, and after that there is a CO2H group, carboxylic group present over there. Here is a methoxy group shown above the plane, and here is a methyl group again over here, and here you can see the carboxylic group, this CO2H, not H, yes, this is a carboxylic group over there, and hydrogen atom we can show here, and one of the amino acid which goes above the plane, amino acid, we know that NH2 group, that is shown over here, and this group and this, they are at equilibrium. This is a equilibrium arrow, or what we can call it as a, just like as a tautomerism type of the things are present over there, and you are going to get this lactone present. And as we know that lactone means what, this acid, not ester group present in the cyclic form, that type of the form are called as a lactone form. And at this corner point there is a NH2 group, and at this point, at this corner point CO2H, there is a carboxylic group, and here you can show at this corner point there will be a methyl group. So this is one of the structure. Now this structure is generally hidden over there. You can show, or you can represent like this. So here will be one skeleton, here you can show here Z, and another one here may be as a one carboxylic group, and here somewhere there is a dotted where the carboxylic group CO2H is shown here, and then this can be joined, that is completely hidden over there, and here you can show N here, and then there will be here, and this type of the skeleton, there you can show is a Y group over here, and then here is a dotted Y group, and then here you can show as a X, and this type of the hidden geometry we cannot see clearly, but it is completely hidden over there, and you have to find by approaching this Chiron approach. These are the things. Now here we can see this one, This can be obtained from this one. I am writing over here. This is again lactone I am showing over here. There you can see hydroxy group OH, and at this point you can show the OH, and here at this corner point there will be a HO, and at this corner point dash dash and then HO, and here again not here is a OH, not the carbonyl group. Here is again is a, but it is a OH, dotted line OH may be there, and now this oxidize. Here you can show there is a oxidize, and at this OH deoxygenated. This one you can call it as a deoxygenate. At this point NH2 retention. Here is a NH2 retention I am writing here, and then carboxylic group. Here is a CO2 group, CO2H, that is a CO2 group retention. Here again retention means what we can call it as a configuration should not change at this position, and here D-glucose deoxygenated. This is a D-glucose, structure of D-glucose here, and this we can call it as a deoxygenate. Deoxygenate. So this is a deoxygenate. It is also as a deoxygenate, so that we will get the final structure of the compound over here. So here a lactone can be easily related to a pyramid carbohydrate precursor. Note how the rule of 5 applied nicely in this case. Rule of 5. Suppose if you see over here 1 2 3 4 1 2 3 4 4 here 1 2 3 4 and 5. How the rule of 5 is applied in this case, that is completely shown over here, and from Tallinn is another example of a target in which a carbohydrate derived segment is fused to the general structure and become an integral part of it. So discovery of amino acids, hydroxy acids and terpene in a target structure. So how that remaining, whatever we have seen so far, all about the apparent, or what we can call it as a partially hidden or completely hidden type of the carbohydrate type symmetry we have found in those structures. So now the remaining 3 amino acid, hydroxy acids and the terpenes, how we can discover here, that is the final point we are learning over here. And it would be appropriate to generalize the concept put forward for discovering carbohydrate type symmetry to other chiral precursor as well. Aspect of amino acid, hydroxy acid and terpene structure were tabulated in terms of that would aid in locating them in the carbon framework of a given target. The sequential alpha amino acid functionality in amino acid, for example, is easy to detect in a target, particularly if a carboxylic group is present. In other instance, a beta or a gamma substituent such as in L-cysteine, L-threonine and L-aspartic acid may provide a useful additional functional complement, particularly if the sense of chirality, which we already learned in our previous lecture, in the precursor and the corresponding segment is the target happen to match. Bifunctional amino acids such as cysteine or aspartic acid may be extended at either end in such a way that the extremity become an integral part of the target framework or ring system. The example, the excellent use of L-cysteine as a chiral precursor to biotin, which we are going to we already seen, but in a shortly we will see we are going to summarize all these things in shortly in a next lecture. So that is a hidden amino acid symmetry present over there. And scheme number 11, this one shows how the carbon framework of L309 or L-aspartic acid can overlap with a portion of the thiomycin structure. Compare D-glucose amino acid are also useful in the synthesis of alpha hydroxy acid by deamination with retention of chirality. Retention of chirality, as we know that. And the synthesis of sulcatol from glutamic acid illustrate the exploitation of partially hidden amino acid symmetry. And among the limitations associated with amino acid precursor are the number of groups, the original chiral center functional group, the choice of chain length of the scarcity, most unnatural amino acids, and moreover conformational bias cannot play a critical role as in the case of carbohydrates. The optical active isomer of hydroxy play a critical role in the case of carbohydrates. And the optical active isomer of dihydroxy acid such as malic acid, tartaric acid share the some advantages and disadvantages as the amino acid, although they too provide ideal substrate when one or two vicinal asymmetric center are short. The tartaric acid have been extensively used in total synthesis, and some examples can be found in the example shown as above, a scheme as for disperser, myosin, etc., where the two asymmetric center and all four carbon atom are utilized. And one inherent feature in tartaric acid is the presence of identical functionality at either end, hence a potential problem is distinguishing on hydroxy group from the other. However, the symmetry encountered in these molecule allows chemical manipulation to provide one and the same product. And terpene can provide carbon framework that are otherwise difficult to construct, and the efficient and the ingenious of minus carvanone and minus camphor in the synthesis of pyrrhotoxicin. It is one of the natural product, a steroid nucleus respectively, are classical example of the discovery of terpenes like framework in these targets. Unfortunately, these useful rigid and flexible templates provide few asymmetric center, and their utility must be exploited in generating chiral cycloalkane or acyclic segment with a predetermined substituted pattern. The enone function in carbon is useful for further chain branching to create a tri-substituted ring, particularly element demonstration of the utilization of optical active precursor in natural product synthesis is seen in the synthesis of cytosaphelin B, where all but carbohydrate type precursor were absolutely used in the elaboration of this intricate molecule means very complicated molecule, and terminant reference for the utilization of amino acid, carbohydrate acid and terpene in natural product synthesis can be found in next. So this all about the specific terpenes. I think with this we have seen this is the extended and the full structure. In the next lecture we will see all whatever we have seen. We will see in short the summary of this, what actually mean by chiral template, and how it is useful in the synthesis of natural product. I think with this let us stop today here. Remaining we will see in the next lecture. Thank you. Have a nice day.